All right, I'm going to throw one more example at you because I did hook myself up with a charging cable, so we got time. We can spend some more time together, quality time. So this one's an FRQ from 2017. It was on both the AB test and the BC test. It was question number 4, which means it was without a calculator. Okay, and this is the famous, infamous, notorious, whatever, potato question. And minutes after, maybe seconds after the exam, um, lots of memes about the internal temperature of the potato. Let's take a look. At time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0, and the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. I copy and pasted this. I did not embellish this at all. Anyway, the internal temperature of the potato at time t minutes can be modeled by the function h, which we don't know, that satisfies the differential equation dh dt is equal to negative 1/4 times h minus 27, where h of t is measured in degrees Celsius and h of 0 is equal to negative 1. Negative what? H of 0 is equal to 91. You can see how I could be tricked into thinking that's negative 1. Anyway, so yeah, we haven't studied differential equations yet, but we have taken derivatives of functions, and especially like, let's say, our implicit equations where we're finding our derivatives, and they're just going to give us the rate at which something is changing, right? In this case, if h of t is measuring the internal temperature of the potato, then this differential equation will just measure the rate at which that temperature is changing at any particular time. Well, actually, at any particular temperature, because there's no time in here. Anyway, okay, so let's take a look at the first couple of parts of this. We can't do the entire question because we don't know how to yet solve this differential equation because it requires some integration. We're not quite there yet, but the first two parts are going to look very familiar. Part A, write the equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at time t equals 3. Piece of cake. You need two pieces of information. You need a point, which is this 0, comma, -1, 91, and you need the slope, which we will get from this differential equation after we plug this point into it. Easy. And then we will plug in 3 so that we could approximate the value of the internal temperature of the potato at time t equals 3. Part B, use the second derivative, not the derivative squared, the second derivative to determine whether your answer in part A is an under-approximate or an overestimate of the internal temperature of the potato at time t equals 3. So remember that that is based on the concavity, which is going to come from our second derivative. Now remember that our argument is not really about 3. It has to be an interval that contains both 0 and 3. Okay, so let's get started on this. And how do I start? I want an equation of a tangent line, so I need a point and I need a slope. The point was given to us. H of 0 is equal to 91, which I will write as 0, 91. So just for clarity here, this is a t value and this is an h value, right? There's no x's and y's in this. Now I also need a slope, so I'm going to write for convenience the differential equation. It's just the derivative, that's all it is equal to negative 1/4 times h minus 27. So let me kind of dissect this for you. So you can see that the rate of this thing is going to be negative, indicating that the temperature of the potato should be decreasing. Doesn't that make sense? You take it out of this hot stove, you put it on the counter to cool, and it should be getting cooler. The temperature should be decreasing. This 27 that's right here is probably the room temperature. Okay. Anyway, so we need to plug in our point, and our point is 0, 91. And as I said, there's no place to plug the 0 in. Doesn't even matter. We're going to just stick the 91 in here. So I will have dh and dt such that t is equal to 0 That's equal to negative 1/4 times 91 minus 27. Given that this is without a calculator, you can say stop that. However, we're going to need this number in a calculation, so it does make sense to do a little bit of arithmetic, which I'm going to do over here. Good old-fashioned arithmetic. 91 minus 27, 8, that'd be 6, 1, 60, 64. Which is totally convenient because 4 goes into that exactly negative 16 times. Now, let's say, for example, you needed to know what the units of this slope was. Well, the Leibniz notation will help you out. Let's see, H is measured in degrees Celsius, and T is measured in, I want to say minutes, so it would just be negative 16. You don't have to write this down because it didn't ask for the units, but if you needed it, negative 16 degrees Celsius per minute, right? The temperature at specifically time t equals 0 is decreasing at a rate of 16 degrees Celsius per minute. Okay, let's put both of those things together in order to write the equation of our tangent line. The whole reason why we came here, tangent line. Y minus 91 is equal to our slope, negative 16 times, not x, I almost wrote an x, t minus 0. Once again, you can leave it like that, but we're going to have to get a local linear approximation of our function of the internal temperature of the potato at time t equals 3. So let's solve this thing for y. Y is equal to negative 16t, and then I'm going to have to add over the 91. There we go. So I'm going to box a couple of things here, like, for example, this tangent line, because it did ask me for it. And then it asked me to use that to approximate the value of the function at 3. So y of 3, actually, here, let me write this, because this is going to be great. H of 3 is approximately equal to negative 16 times 3 plus 91. That's a negative 48 plus 91. Once again, that is safe stoppable, but I'm gonna do some arithmetic. All right, borrow the 1, 8. That makes 43. 43, I'm gonna put units, even though it didn't call for them, there we go, 43 degrees Celsius. So point breakdown went like this. The slope was worth 1 point. The equation of the tangent line was worth a point. And then your linear approximation of the internal temperature of the potato at time t equals 3 was worth your third point for that one. Now, we're not quite finished because part B asks us to use a second derivative in order to determine whether or not we just over or under approximated, t of 3, h of 3, I should say. So in order to do that, we need to find the second derivative. So I'm gonna, for convenience, rewrite the first one, which was a negative 1/4 h minus 27. Okay, so what if I just were to distribute this? Negative 1/4 h and then plus 27 over 4. I did that because I'm going to have to take the derivative, and this part's going to go to 0, but I still have to take the derivative of this part. Okay, and then realize that I'm going to have to do so implicitly because this is our dependent variable, and our derivative has the dependent variable in it. Think of this as a y and this one as a y, so we're going to have to use the chain rule on this. So d2h dt is equal to negative 1/4 dh dt. All right, as we have seen, you absolutely, at this juncture, want to do some sort of substitution right here. And I forgot something. Nah, I didn't. I need to substitute the original derivative in for dh dt. So here is the negative 1/4 times dh dt, which is another negative 1/4 times h minus 27. And multiply our fractions together, we get a positive 1/16 h minus 27. And so here is our second derivative. Boop. Okay. So of course I can't stick in, there's no way that I could stick in a t equals 3. And I don't even know what the value of h is at 3. All I have is like this approximation. So how am I supposed to know whether or not the function is supposed to be concave up or concave down? That is the reason why back over here on the original stem, problem stem, it says this. Here, I'm going to highlight it for you. The internal temperature of the potato is greater than 27 degrees for all time t equals 0. So h is always greater than 27. H is always greater than 27. So since h is always greater than 27, this thing, this set of parentheses right here, is always going to be a positive number. This thing right there is always going to be positive. Whoop, whoop. Since it's always positive, and you're multiplying it times 1/16, the value of the second derivative will always be greater than 0 for t is greater than 0. Okay, so I'm going to write stuff like this. For, t greater than 0, dh, d2h, dt2 is greater than 0 since h is greater than 27. Well, what does that mean? Okay, so remember, second derivative is positive. That means that your function is concave up. If it's concave up, draw yourself a little picture here. We have a tangent line which just under approximated the value of the function. Okay, so just write that up in here. Since for t is greater than 0, second derivative is greater than 0, since h is bigger than 27, and h must be concave up for t is greater than 0. And I'm just going to put lots of, this is a run-on sentence. There's no commas here, just a whole bunch of ands. Just let's hope that no English teacher is going to be grading this. Let's see. And let's see, the tangent line under approximates the, I'm going to write it now, internal temperature of the potato at t is equal to 3. Voila. And guess what? You know, all of that work, finding the second derivative and drawing the conclusion, all of that, whoa, I just cut off part of my answer. It was worth exactly just 1 point. Where are all the other points? Well, all of the other points are on part C. Let's just go ahead and look at it. Sneak preview. For time t is less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation, and then it gives us a differential equation there, where g of t is measured in degrees Celsius and g of 0 is equal to 91. Find the expression for g of t. Based on this model, one more time, what is the internal temperature of the potato at time t equals 3? So we don't have the tools necessary to actually find what g of t is because it involves solving this differential equation, particularly at 0,91, which needs some integration. So there you go. We were at least able, as a very nice application of tangent line approximation and concavity, to be able to do at least the first 2 parts and get ourselves 4 out of those 9 points. Coming your way soon, and by soon I mean next year sometime, we will learn how to do the integration necessary to solve that differential equation. So in the meantime, local linearity, we were able to use the tangent line to approximate the values of a function near the point of tangency and also use the function's concavity to be able to tell whether or not our approximation was an over or an under approximate.